So whatever we have learned till now, quantum mechanics or crystal structure, we are going to make the use of that now in the theory of this band theory of the semiconductors, how the bands form, how the electron behavior is inside a crystal, and density of states, etc. Right? So we start from here, the band theory, and slowly we will be moving towards our electron density, typical semiconductor properties that you might have learned in your previous classes, right? So typically you start from the electron density there. Don't talk much about the bands, but we will go through that in detail, and we'll see how the expression of the electron density and all of that, density of states, etc., that's related to the quantum theory of the solids of the semiconductors. Okay, so let's start with the simple one-dimensional crystal lattice again. So in a one-dimensional crystal lattice, you know that the atoms are arranged in an 1D array, and say the lattice constant is A, or you can also say this is the primitive vector, right? The magnitude of that. And I'm assuming that it's a very simple atom, just one electron atom. So this is the atomic core, and there will be one electron which will be revolving around that, and I have arranged several such atoms in 1D. So if I talk about, say, one electron which is inside this atom, what kind of potential that electron will see? Say if this atom would have been, say, isolated, it's not in an array, so what kind of potential that electron will see? We have seen that. So it's going to be an attractive Coulombic potential, right? So you have a positive charge on the nucleus, and then you have the electron. So you have a positive charge, and then you have an electron. So what kind of potential it will have? So say the distance between them is r. So we know that the potential is going to be inversely proportional to r, the distance. We have seen this. Okay, and accordingly, what kind of attractive potential we will get? So it will look something like this. So this is the potential when you go far away from here, right? So at 0, this atomic core is located, positive charge. If you go far away from it, so the potential energy becomes 0, right? R becomes infinity. I'm assuming the infinity as the reference. You can take any reference, but usually we take infinity as the reference. And then when you come closer and closer, so this becomes more and more negative, and it shoots up at the location of the positive charge, right? R becomes small, so, and this is going to be a negative quantity, right? So because if you look at the full expression, so it's going to be V is equals to 1 upon some 4 pi epsilon into this charge into this charge, right? So it will be minus q square by r. So it's a negative quantity, right? Q1, Q2 by r. So that's why an attractive potential, right? And because r becomes very small, so this becomes minus infinity. So this is the potential of one atom due to one atom. But there are several such atoms stacked in an array. So how will, say, the combined potential of, say, these two atoms will look like? Say we only consider, say, these two atoms. So how will it look like? So potential is a scalar quantity, you know that, potential energy. So it will be simply the sum of potential due to this plus potential due to this. So it will look like this. Okay. So you sum this, again you sum this, and then it will look something like this. Okay. Similarly, you can calculate the potential of the total array. You simply take the algebraic sum, and you get something like this. Okay. So inside, if you are well within the crystal, it's a periodic potential. It has a periodicity. What's the periodicity? A. So it's repeating after every A. At the surfaces, so because beyond this you don't have an atom, beyond this you don't have an atom, so that's why you are seeing this higher potential here. Okay, so it's coming because of this branch. But within the crystal, if I am assuming that my number of atoms are very large, so in the bulk of the crystal I won't see these surface effects, so potential will be almost periodic. Okay, so electron is going to move in a periodic potential when we talk about a crystal. Okay, so now I'm going to be making some approximation so that our analysis becomes easier. To understand the concept of energy band, so we will have to make some approximations. So what I'm going to do, I have this kind of a potential due to one atom, right? And you know that atom will have energy levels, right? E1, E2, E3, E4. So this is the ground state and first excited state, second excited state, and so on. So I'm going to approximate it with something that we know. So in the lectures that I provided, I talked about a square potential, finite square potential and infinite square potential. So those are the potentials that we already know. We have worked with them. So let me approximate this thing as this. Now, it's not a very good approximation, but qualitatively it's going to retain all of the properties. Okay, so there are these energy levels. So there are these energy levels, right? So electron is confined within an attractive type of a potential here, right? Say if this is V equal to 0, so this is negative, right? Negative potential, and electron is trapped here. And it will have some energy levels, of course. And if it is finite height, so it will have finite number of energy levels. Okay, so after making this approximation, now let's talk about just two atoms, a simple diatomic molecule. So in a diatomic molecule, what will we have? We will have two square potentials. So each atom I'm going to be approximating by one square potential. So say these atoms have not formed a diatomic molecule yet. So they are far apart. Okay. So two identical atoms and they are far away from each other. And of course they will show identical discrete energies because they are identical atoms. So something like this. So you have two square wells. So this is the atom number 1, atom A, atom B, and they are identical. So identical energies, right? Identical wave function. So this is the ground state wave function. You know that so the wave function it's going to be E1 odd, then E1 odd, right? It will go like this. And if you have a finite square potential, so some of the wave function will also leak here. If this would have been, say, infinite potential, so the probability of finding the electron outside the potential well would have been 0. But because this is finite, some of this will leak. So there is a finite probability of finding the electron outside this well as well. Okay? And similarly here, as you go higher and higher in energy, you can see that the extent of this decay, it keeps spreading more. So this spread is larger than this. Okay, this spread is even larger than this as you are going higher and higher in energy. Can you tell me the reason? Any reason for this? Electron what? Yes, or in other way we can say that when the electron is at a lower energy state, so it's much closer to the nucleus. I mean, it's an atom, right? So it is very highly attracted. So it is confined within this space. As it goes higher and higher in energy, it gets more flexibility. It's going away, right? It's going higher in energy from the negative attractive potential. So it goes larger and larger into these areas. Okay. So similarly, we have this atom as well, and this B is the distance between them. A is the extent of the well. So B is infinity here. and they are not talking to each other. Yes, yes, so it can leak, but by the time it reaches here, the probability is already 0, right? So this wave function is decaying like this, but the probability of finding this electron far away from here will be 0. It's exponentially decaying almost. Similarly, probability of finding this electron far away will be 0. So this electron is going to be confined to this well. The electron here is going to be confined to this well. They are not talking to each other. They are localized. Okay. So what will I next do? I will bring them closer. So I am going to decrease the B from infinity. Okay, so let's bring them closer. Now the situation will look something like this, right? So you have A, and then you have some B, and then you have A. And B, say, I mean, in the picture B looks smaller than A, but let's assume that B is still much larger than A, but it is not infinity. Okay, so what will happen? So when we bring these two wells together, what happens is that the wave functions are going to talk to each other. So the wave function here, which was leaking like this, it can reach here. Similarly, the wave function which was leaking like this, it can reach here. So there is some finite probability of, say, this electron to be found in this well. There is finite probability of this electron to be found in this well. Okay, so the electrons that were localized, they have become delocalized now. They are not just confined to one particular atom. There is some finite probability that this electron, say if I conduct an experiment and it has, say, say 1,000 trials I do. So in most of the trials you will still find the electron here, but at least in some trials you will find that the electron will be here. Electron of atom A will be found in atom B. Okay, because there is some finite probability. So they have become delocalized. So what will be the situation? Because they have delocalized, so these wells they start to interact with each other, and the energy levels that were there in isolated atoms, they will not remain the same. There will be splitting of energy levels. Okay, so something like this. So say this was the ground state, this was the ground state. When you bring these atoms together, so there will be some small splitting. So one level will go up, other will go down. Okay, so these single identical ground states will split into two energies, E1 and E2, which will be some distance apart. There will be some splitting because of the coupling. Now the full full-blown quantum mechanics treatment of this problem is possible. You can calculate from Schrodinger equation that yes, there is actually E1 and E2, but we will mostly go qualitatively. Okay, we won't go into the mathematics of that. So if you solve the Schrodinger equation, you will find that there is an E1 and E2. There will be some splitting. Okay. So one electron will go in the ground state, another will go in the first excited state. Okay, two electrons, so you need two energy levels. Similarly, the higher levels. So this was the first excited state. It will also split in energy. So E3 and E4, and the splitting here is larger. Okay, so basically these are interacting more. You saw that the extent of the wave function outside this attractive potential was larger. So because these levels are interacting more, there is larger splitting. Okay. Similarly, these levels, they interact even more. So there is even larger splitting. E5 and E6. Okay. So now you can't say that this atom is isolated, this atom is isolated. So they have formed a system in which the energy eigenvalues are E1, E2, E3, E4, E5, E6. It's not an isolated atom A and isolated atom B. It's a system now. Okay, now let's also look at the corresponding wave functions. So the wave function, when my B is not infinity but it is still much larger than A, so it will look like this. So this is the wave function in atom A, wave function in atom B. So it's going like this, it's going like this, right? So it will look something like this. Okay, so this corresponds to the ground state E1. If you look at the E2, so how does it go? Because it's a symmetric potential well, right? So your wave functions are going to be like E1 odd, E1 odd, E1 odd. So if this is E1, the ground state, the next state will be odd. Next state is E2. So that's why it is an odd. Okay. So this is for B much greater than A. If I bring them even closer, so you will see that there will be even more overlap. Right. So you can still, say that, yeah, this is electron in atom A, electron in atom B, but here you can't say that, right? So they are overlapping much more. So this is psi 1 and this is psi 2. Okay, E1 odd. So that's what happens, and approximately, if you look at this, so approximately this psi 1, it is nothing but psi A plus psi B, approximately. Okay, so psi A means the electron wave function in atom A, right? Electron wave function in atom B when they are isolated. So if you can simply sum them up, so that will make your psi 1 approximately. Yeah, full calculation you will have to do through the Schrodinger equation, but this approximation is good. So this type of interaction, it promotes bonding. Why? Look at it. So say B is approximately equal to A. We look at this case. So the probability of finding the electron in between the nuclei. So this is nucleus 1, nucleus 2, right, at the center, here. But in between the nuclei, the probability of finding the electron is finite now. Okay, mod psi square if you take, so there will be finite probability of finding the electron. So this type of interaction, it's promoting the bonding. What's a bond? Bond means the probability of finding the electron in between the atoms, it becomes much larger than finding those electrons at their respective atoms. So it's doing something like that. Okay, what about this case? This or this? This is approximately psi A minus psi B, and this promotes anti-bonding. Why anti-bonding? Probability of finding the electrons at the respective nuclei is now even more larger. I mean, it's even larger than it was in an isolated case. Isolated A, isolated B, right? So the probability you can see of finding the electron, if you say the mod psi square, so at the nuclei, this and this, the probability of finding the electron will be larger now, rather than in between. In between, the probability is 0. It can't form a bond. So that's why anti-bonding. Have you heard these bonding and anti-bonding before? People from, say, chemistry. Have you heard of molecular orbital theory? Right? Formation of bond. So it's exactly that. It's called linear combination of atomic orbitals. Okay? So there you talk about, sigma bonds or sigma pi or whatever. Okay? So it's coming from the quantum mechanics. And it's a simple approximation I've shown. So that's why I'm talking, it's a simple first order crude model of diatomic molecule. We have seen now 2 atoms. Let's now put more atoms in place, more potential wells. So we have seen single, we have seen double. Let's talk about 1, 2, 3, 4. So when you had 2 wells, there was splitting of energy levels in 2 levels. If you have 4 such potential wells, so the splitting will be into 4 levels. Okay, it can be proved. So the ground state will split into 4 levels, first excited state will split into 4 levels, and so on. So these are closely spaced levels and they have split. Can you see where I am moving? Can you see? Can you see some range of energies? This. What if I have a large number of atoms which are talking to each other in a crystal? Right? So the electron is not isolated. Electron is not confined to just one atom. It is not the property of one atom. It becomes property of all the atoms in the crystal when they form the bond. So in a crystal, when you have a large number of atoms, so say if I have 100 atoms, so how many energy levels will be there? For one identical state, the same level, there will be 100 such levels. Say if I have 10 to the power 8. 10 to the power 8 levels, closely spaced 10 to the power 8 level. Will you be able to differentiate between them? No, they will be so much, because you have to put those energy levels in a finite energy space and they are so closely packed, you can't even differentiate between the levels. Yes, the levels are still there, right? So they form an energy band. So energy band, it's a closely spaced packed energy level in a finite energy space, you can say. So say I have several atoms, right, and this is the ground state energy. Now the ground state energy, we know that it does not split easily. It's much more closer to the nucleus, right? So the electrons will not be talking to each other too much because each electron is very close to the nucleus. So that's why the splitting is not that much. It splits when my interatomic distance becomes very small. Okay, now look at this, n equal to 2. Now I'm talking about the levels of atoms. So when you bring them closer, interatomic distance, if you keep decreasing, so they will start to split. Similarly, n equal to 3, they will start to split even more. So at some particular distance, the energy of the system will be minimized. It will have the minimum energy, and that will become your R0, the interatomic distance for which your system is stable. Okay, now at that R0, you can see that for n equal to 1, there is almost no range of energy. If you zoom it out, you will still see some range of energy, and this is the range of energy, and there are so many closely packed energy levels here. And then you have this, right? So all of these are bands, band corresponding to ground level, then this is an energy band, and this is an energy band, and so on. Okay, so these are energy bands. You can also see that there are some gaps. So when I am going from here to here, so band 1 to say band 2, I don't have an energy state here. What's the reason? Because I started like this. I started with energy levels which were not continuous. They were some distance apart. And because there is some distance between them, this spread, this also spread, but they did not overlap. I mean, in some atoms they can overlap and then again split, right? But I'm talking about a very simple situation here. So because of that, you see this gap, because there was a gap to start with. Okay, similarly, you see this gap. So these are called forbidden energy gaps. Okay, so this is basically the qualitative description of how the bands form. So now we will move to some quantitative description. Okay, so the next is Bloch theorem. So what is Bloch theorem? So again, you have a crystal. It can be 1D, 2D, 3D, whatever, doesn't matter. It can have complex potentials. Okay, so Bloch theorem says that. So Bloch theorem says it gives you the energy eigenfunction, the properties of the energy eigenfunction. So if I have, see, we have done some simple problems, right, and we have calculated energy eigenfunctions. So say for infinite potential well or finite potential well, we should solve the Schrodinger equation. We get some energy eigenfunctions, energy eigenvalues, right? So Bloch theorem tells you that the energy eigenfunctions for a periodic potential will have certain properties. Okay, so what is that property? Say if ux is a 1D periodic potential and the period is A, the eigenstates or eigenfunctions of the Hamiltonian, right? You know that, yeah? This thing, basically the solution of the time independent Schrodinger equation, that's what it is, right? Are given by this. So they will have this property. So if psi denotes an eigenstate, so it's going to follow this property. What's the property? Psi of x plus a will be equal to psi of x into e to the power iota k a. K is some number and it has the dimension of 1 by length. No, because e to the power this argument must be dimensionless. So if there is an a here, so k should have 1 by a, right? So it's some kind of a wave number. Now it may not be exactly 2 pi by lambda, okay, but it's some kind of a wave number. So psi of x plus a is equals to psi x into e to the power iota k. I'm just going to give you some idea how, there is a full derivation of that, a formal derivation. We won't go into that theory. It requires some more complicated quantum mechanics, operators and stuff. But I can give you some idea why this is there. Okay, let's talk about some observables. Say you have a periodic potential, yes, and let's talk about the electron density. Now, electron density will be proportional to mod psi square. Mod psi square gives the probability of finding the electrons. Yes, so electron density is what? The number of electrons per unit volume or per unit area, whatever. Okay, so electron density is definitely related to mod psi square, because mod psi square gives you the probability of finding the electrons, basically how many electrons, right? So in a periodic potential, if I move say from here to here, and I don't have an externally applied electric field, so I have a semiconductor slab say of silicon, and I don't apply an electric field there. So if I move say from here to here, do you expect the electron density will change? It won't. It has to be periodic. It has to be periodic. Yes. There is no reason for that, right? Unless you go to the surfaces, we are not talking about that. In the bulk of the semiconductor, electron density here and here, they must remain the same. It must remain the same, right? So it means mod psi square here and mod psi square here. So mod psi square must be equal to this. Yes? Can you now see what I am trying to say? What if I take the mod here on both sides and square it? What will happen in equation number 1? Right? This is equals to square. What will happen to this? This will become 1. Mod of e to the power iota k, that's 1. Right? So this is actually giving me this. This is what I want. So Bloch theorem is kind of giving me that periodicity property. Okay. This is not a formal derivation, just to give you some hint. Okay. Equivalently, there is another definition of the Bloch theorem. You can express it in another form as well. So, which is this. So, if I have a wave function which follows this, so equivalently you can write that the wave function will also follow this. So, what is this? So, psi x will be equal to some e to the power iota kx. This k is the same as this times some ux, and ux is any periodic function. Ux is a periodic function and its period is a. Okay, we will see that how these two definitions are equivalent. So, so this is what I mean. Okay, ux is a periodic function and it has the same periodicity as the crystal. It means u of x plus a is equals to u of a. That's what I mean. Okay, so if you look at the definition too, so the wave function, the eigenstate is going to be e to the power iota kx. So what is the e to the power iota kx? What is it eigenstate of? In a free particle case, what was the eigenfunction? E to the power iota kx. Right, so this represents a plane wave. But when you put the same free electron in a crystal, so you have the plane wave, but it is modulated by a periodic function. And this u of x, it depends upon your material, your crystal structure and everything. So this is what is making it different from a free particle case. Free particle is e to the power iota kx. When you put the same electron in a crystal, it is e to the power iota kx times this modulating function, which is periodic. Okay, so it will look like something like this. I mean, because these are complex numbers, so we can only talk about the real or imaginary part. So real part of say psi x, it's going to look like this. So this is a e to the power iota kx property, right? It's a plane wave, and because of this ux, it will be modulated. So these oscillations, all of this that you see, it's coming because of this ux. Okay, so the total wave function is this, and it has been achieved by modulating this plane wave by ux. Okay, so now let's see how these definitions are equivalent, and then we will take some break. So let's start from this definition. So u of x is equals to e to the power iota kx into ux. We know that, right? Let's say I replace this x with x plus a on both sides. I can do that, yes. So psi of x plus a will be e to the power iota k x plus a and u x plus a. Yes, u x plus a is ux, I know that, and I can split these into these two factors. So this is e to the power iota k into e to the power iota kx. What is this? E to the power iota kx into ux. This is nothing but psi of x. So that becomes psi of x into e to the power iota k. So which is the definition number 1. Both are equivalent. Okay, and this is not only for one dimension, it is valid in 3 dimension. So for 3D, the theorem can be extended as psi of, so instead of x there will be position vector r. So it's the position vector, I mean of any point in the space, plus instead of a, so a is like a primitive vector or periodicity. So what is its analogous in the 3D? So that will be vector r. So vector r is any lattice vector in the real lattice, right? So it's the position vector of any lattice point. So psi of vector small r plus capital R is equals to psi of small vector r into e to the power iota k dot r. So instead of because now k will not remain a number in 3D, it will also become a vector, a wave vector instead of simply a wave number, right? So it's a wave vector and this is vector r, so there is a dot product in between. Okay, or you can also write this definition in the other form, e to the power iota k dot r into u of r. U of r is again a periodic function of this r. So let's talk about the boundary conditions. In Schrodinger equation, we always have some boundary conditions, right? So in an infinite potential well, finite potential well, we know that. So the boundary conditions are always needed because it's a differential equation, right? Bloch wave functions are also the solutions of basically the Schrodinger equation. So to get the complete picture, we will need some boundary conditions. Now, in crystals, there is a problem. So the information about the boundaries is usually lacking. So surface can be quite complex. So the boundary condition, the exact boundary conditions, finding that out can be quite challenging. Okay. But the good thing is, if you only say, if I have say bulk semiconductor, right? It's say a piece of semiconductor. So the properties of the bulk of the semiconductor, they are unaffected by the surfaces. So what happens at the surfaces does not matter what happens within the bulk of the semiconductor. Okay, because most part of the bulk of the semiconductor, it's away from the surfaces. So it doesn't matter. Okay, so that gives us some flexibility to choose some convenient boundary conditions, because the properties of the bulk are not affected much, and we will choose the boundary conditions that are going to be easy to work with. Okay, so what kind of boundary conditions we have already seen? Say in an infinite potential well, what kind of boundary conditions were there? We assume that at the infinite boundary, wave function has to be 0. It's a hard boundary condition. Hard boundary condition means you are giving the wave function some value. It has to be this. Okay, say psi equal to 0. So the hard boundary condition will be, we assume say psi equal to 0 at the surfaces. But is that something which is workable? First of all, these boundary conditions may not represent the real potential at the boundary. Okay, psi may not actually be 0 completely at the boundary. The second thing is, this type of boundary condition, which is hard boundary condition, this always results in some kind of a standing wave solution. Standing wave solution means, so when we solve this, you see there is some a sin kx plus b cos kx. So there is some interference of the wave. So it forms some standing wave. It's not like a plane wave. Okay. So it will have sine and cosine type of quantities, and they can be actually very difficult to work with compared to say e to the power iota kx. They can be actually, sine and cosine can be difficult to work with. So for example, you get a solution like this here, right? Under root of 2a sine n pi x over a for infinite potential well. So it's not something which is easy to work with, sine and cosine. So we usually do not employ these hard boundary conditions. What we do, we apply something called periodic boundary condition, or it's also called Born-Karman boundary condition. So what's a periodic boundary condition? So periodic boundary conditions, as I said, it's basically, it's a convenient set of boundary conditions so that our problem becomes solvable. I know that bulk of the properties are not much affected by the surfaces, so I have put some boundary conditions which are convenient to work with, and if I apply those boundary conditions, my problem becomes solvable. Okay. Now the periodic boundary condition, what does it mean, periodic boundary condition? So periodic boundary conditions will basically remove the role of the surface altogether. So it basically means when you incident an electron wave on the surface, it comes out of the other surface. So that's what the periodic boundary condition means. It's the surfaces, say two surfaces are there, they become periodic. The wave function value at the one surface becomes equal to the wave function value at the other surface. So it's going at one surface and it's coming out of the other surface. Okay, so it's like if you have, say, 1D crystal, right, and it has n atoms. So you have basically the periodic boundary condition means that I have tied these two ends together. It's like a ring now. Okay, so the wave function here is equal to the wave function here. That's what I'm assuming. Now I know that this is not the reality, it may not be the real picture, but it's convenient to work with, and it has been found that the solutions which are obtained from the periodic boundary conditions, they reasonably well can explain the experimental results. Okay, and that's why we are going to go with these conditions. Mathematically they will be easier to work with. So this is what I am trying to say. Psi of x plus L will be equal to psi of x. Okay, so this is equal to this, or any x, say I have this psi of x. So psi of x is equal to psi of x plus L. Okay, if you are, say, talking about, say, if I've converted this into a ring, so say this is x and then x plus L is again the same thing. Or L you can also write L in terms of the number of atoms and the period. So if this is the length, what will be the L? And the distance between the two atoms is a, so that L will be equal to n times a. Obviously, you can also write psi of x plus Na is equals to psi of x. Okay, so from now onward, I'm going to be using this periodic boundary condition. And now let's talk about what is this K? Allowed K states. Again, I'll go back to infinite potential well, right? So by applying the boundary conditions, what did we get? Allowed energies, energy eigenvalues, h square k square by 2ma square, or you can also say allowed k values. Okay, actually we get a k first and then we put that in the energy, so you get the energy values. So by application of these boundary conditions, we will be able to calculate the k states which are allowed. It's not that every k is allowed, only certain k's are allowed. What are those k's? So for 1D, let's keep our discussion limited to 1D and then I will generalize it for 3D. So psi of x plus Na is equals to psi of x, I know that. Yes. From the Bloch theorem, I also know that psi of x plus Na is equals to e to the power iota k Na into psi x, right? So psi of x plus a is equals to e to the power iota k a into psi x, and I have replaced that a with Na, so that will be e to the power iota k Na. Okay, it's not that you can put any number here. Okay, because it's a multiple, integral multiple of a. That's why I can use that. Only the integral multiple of a's are allowed. A, 2a, 3a, 4a, right? It's not that you are putting 1.5a and that will still work. No. It can be proved, by the way. If psi of x plus a is equals to e to the power iota ka into psi x, so psi of x plus 2a, you can prove that it will be e to the power iota 2ka into psi x. It can be proved. Okay, you will have to basically keep applying this Bloch theorem again and again, so you will get this form. Okay, so what do I get from equation number 1 and 2? This has to be equal to 1. Compare equation 1 and 2. So e to the power iota k Na, it is equal to 1. And this is my condition. And this will determine the allowed values of the k. If e to the power iota k Na is equals to 1, what should be the value of the k? So this part must be some integral multiple of 2 pi. E to the power iota some integral multiple of 2 pi will always give you 1. We have seen that so many times. So k will be equal to, so this kna is equals to 2 pi n. So k will be equal to 2 pi n divided by na, where n can be any integer, 0, plus minus 1, plus minus 2, and so on. No restriction. Okay. So these are all the allowed k values. Now the spacing between them will be actually small, because n is in an actual crystal can be a large number, right? So by the way, what will be the spacing between any two k values, any two adjacent k values? So say 2 pi by na, and then you have 2 pi, say n equal to 1, you have already used n equal to 2, so that will be 4 pi by na. 4 pi by na minus 2 pi by na, it gives you 2 pi by na. So any two k values will have a spacing of 2 pi by na. And if this n is very large, so spacing can be quite small. Okay, so sometimes that's why we sometimes consider this k as a continuous number also, because the spacing between adjacent k values is very small. So it's almost continuous then. Okay, so let's see how does this k relate to my crystal structure. Okay, in the crystal lattice we have understood so many concepts. Reciprocal lattice we saw, direct lattice, reciprocal lattice, and primitive cells. So what's the use of all of that? We are going to make the use of that now. So let's say I'm talking about 1D lattice and how my k relates to this reciprocal lattice. Okay, so say I have 1D real lattice and the primitive vector is vector A is equals to Ax cap. A is the distance between them. So primitive vector will be simply the magnitude into unit vector Ax cap. That's what my primitive vector will be. And what will be the corresponding reciprocal lattice? Can we make it? How do we convert the lattice into reciprocal lattice? I mean, it's a simple 1D lattice, so it's easy. If it is more complicated, so you use those formulas of B1, B2 and B3, but in this case it's going to be easy. So it's simply what will be the distance between, say, two lattice points in the reciprocal lattice? 2 pi by A. Yes? So if this is A, so in the reciprocal lattice this becomes reciprocal, but with the 2 pi by A. So reciprocal lattice vector is primitive vector B is equals to 2 pi by A into x cap. Now what's the relationship between this k and, say, this reciprocal lattice? We are going to establish that. Now why this k is related to reciprocal lattice? So see, look at this primitive vector. It has a dimension of 1 over length. K also we know that it's some kind of 1 over length. Okay, so let's try to express that k in terms of b, because they have the same dimension, so they represent basically the same thing, at least dimensionally. Okay, so we can try to express k in terms of b. Let's do that. So for 1D we know that this k is 2 pi n divided by na. We just saw that from the Bloch theorem and the periodic boundary condition. So 2 pi n divided by na x cap, that will be my k vector in 1D. Okay, 2 pi by a and x cap, what is this? This is b. Yes, so what's the relationship between k and b? It is this. So k is equals to n by capital N into b. Okay, so it can be directly related to the reciprocal lattice vector. Yes, so this is any integer and capital N is the number of atoms. And this is the simplest case, which is 1D. Now can you tell me the number of k values? Oh, by the way, this k is larger than b or smaller than b? So n we start from 0, 1, 2, 3, 4, right? Capital N is a quite large number. So in general, it of course it can be larger if you take n beyond n. But say if n is less than capital N, we limit ourselves to that case. So k, vector k will be, magnitude of that will be less than b. Okay, so in one primitive vector, I can fit several k vectors. That's what it means. True? The vector b is larger than vector k. Let's see how many we can fit. Can you tell me how many we can fit? In one vector b, how many k's I can fit? I mean, see, look at the length of this. So this is 2 pi by a. What's the length of k? So this is 2 pi by a. What's the distance between two adjacent k points? 2 pi by na. We know that. Between two adjacent k's, it will be 2 pi by na. So say I start from here. So 0, n equal to 0, right? N equal to 1, so that will give me 2 pi by na. Somewhere here, n equal to 2 will give me 4 pi by na, 6 pi by na, 8 pi by na, and so on. For how large n I can go, so that I don't cross this. N equal to n. So because for n equal to capital N, it will be 2 pi by a, which is equal to b. Okay. How many k? So the total length of this divided by the distance between two adjacent k points, that will give me the number of k points. Correct? Total length divided by the distance between any two k points, which will be here. So what will be that? 2 pi by a divided by 2 pi by na. Yes. So that is capital N, which is equal to the number of sides in the real lattice. You see, in one reciprocal lattice, in one primitive vector of the reciprocal lattice, you can fit capital N number of k's, n points. What is n? N is the number of atoms or number of lattice points in the real lattice. Okay. So this is going to be useful for us. Whatever I am teaching, it's going to be useful later. We are just building some stuff before we reach the actual band theory. Now this property can be extended to the 2D also, right? So I'm just going to quickly go through the 2D, but 3D I will not talk about. I will simply give you the result. So if we have, say, k in the 2D reciprocal lattice space, so say I have a rectangular real lattice. Okay, so this is a1, a2, two primitive vectors. So a1 x cap, a2 y cap, and the length along the x direction is L1 equal to n1 times a1 and L2 equal to n2 times a2. So n1 atoms are stacked in this direction, n2 atoms are stacked in this direction. So this is totally a grid. It's a total grid. Okay. And how many atoms will be there in this total grid? This. How many atoms are there in this total grid? So this is n1, this is n2. Total atom will be n1 into n2. Okay, so number of sides here are n1 into n2. Now what will be the corresponding reciprocal lattice? So it's a rectangular reciprocal lattice, so it's easy to do. Simply, so this a1 becomes b1, 2 pi by a1, and a2 becomes b2, 2 pi by a2. Yes, so this is the reciprocal lattice. Okay, so as we saw in case of 1D, k can be expressed in terms of primitive reciprocal lattice, right? Vector b. So here I have b1 and b2. So again, vector k can be represented in terms of b1 and b2. How? So k will be equal to some x1 into b1 plus x2 into b2. What are x1 and x2? Very similar to what we had in the 1D case. So x1 is going to be equal to n1 is any integer divided by capital N1. Capital N1 is the number of atoms stacked in this direction, x direction. Okay, and N1 is equals to 0 plus minus 1 plus minus 2, whatever. And x2 is n2 by capital N2. Capital N2 is the number of atoms stacked in this direction. the y direction. So it's just an extension of the 1D. In 1D we only had B1 and X1. Now I have B2 also, and X2 is this. Simple extension. Okay, it can be proved. The proof is on the next page. You can go through it on your own. Not a very difficult one, but I won't cover it. So this is what my reciprocal lattice is going to be. The relationship between the K and the reciprocal lattice is going to be. And one thing to note is that this x1 and x2 are not necessarily integers. Okay, x1, it's not like it's an integral multiple of b1 plus integral multiple of b2. You can clearly see that x1 is n1 by capital N. It's not an integer. n1 is an integer, but n1 by capital N it's not an integer. Okay. So don't think that this is a reciprocal lattice, because in a reciprocal lattice, if you want to find say the position vector of any point, so that will be integral multiple of b1 plus integral multiple of b2. Vector G that I think we saw. So that is m1 b1 plus m2 b2, where m1 and m2 are both integers. Here that's not the case. So this K may fall somewhere in between also. It is not that it has to be necessarily one of the sides here. No. So K can fall, say, somewhere here, in between. It can be anywhere. But it is restricted still. How is it restricted? Because x1 and x2 are given by this and this. And only certain values are allowed. Yes? Okay. So this I won't go through. This is the derivation. You can, if you want, you can go through it. It's optional. Won't be asked in exam. Okay, so let's now try to find out how many K values I can have in one primitive cell. So in one primitive cell, how many K values were there? N. In 1D we saw that. Now can that concept be extended to the 2D also? Let's quickly see that. Okay, then in the 3D again, I will simply tell you the result. So this is my reciprocal lattice, and I know that K is x1 b1 plus x2 b2, and x1 is n1 by n1, capital N1, n2 by capital N2, right? Okay. Now for a rectangular lattice, we know that this b1 is going to be what? 2 pi by a1, right? And this is n1 and this is capital N1. So the total quantity is this. And b2 is 2 pi by a2 into y cap, right? And the rest is coming from here, n2 by n2. Okay. So this was in terms of b1 and b2, but I have converted that into x and y. So this is some coefficient kx and this is some coefficient ky. So kx x cap plus ky y cap. Understood? Okay. I have simply put the values of the b1 and b2. Now I can keep varying this n1 and n2. They are integers, and I can generate many values of the k, right? Depending upon what kind of combination I have of n1 and n2. So n1 can be 0 plus minus 1 plus minus 2 and so on. Similarly n2 can be plus minus 1 0 1 whatever 1 2 3 4, right? So I can generate a full k space here. Every combination of n1 and n2 is going to give me 1 k point. Okay. Yeah, I wanted to show you this. So if you generate n1 and n2, n1 and n2, if you keep varying, you will be able to generate this smaller grid. So you have a bigger grid, which is the reciprocal lattice, but this smaller grid that you see, it is actually corresponding to this k. So every point at the intersection of this grid, it represents 1 k point. It has been generated through some combination of n1 and n2. And we know that this n1 and n2 are large, so that's why this is a smaller grid. Yes. Now what I want to calculate, I want to know, so 1k vector, say this. So this represent 1 point, and one small square, I can associate one small square with one k point, like this. So if I have say one k vector here, right? So I can associate that this square correspond to this. Okay, so then I have say this k vector, and this square correspond to this. So the number of k points and the number of squares in this space will be equal, right? So number of k, one k point will give you one square. Okay, how many small squares are there in this larger area? So what's the area here? 2 pi by a1 into 2 pi by a2. Here, the bigger area, 2 pi by a1 into 2 pi by a2. And what's the area of this small grid? Small square. So small square is, what's the distance between two, say, if I simply go in the x direction from say here to here, this, okay? So this remains constant. So what's the difference? 2 pi by n1 a1, right? Say n1 for n1 equal to 1, and then n2 4 pi by n1 a1. So the distance will be 2 pi by n1 a1, this small distance. Similarly, if I go in this direction, the distance will be 2 pi by n2 a2, correct? So the area of the small cell will be 2 pi by n1 a1 into 2 pi by n2 a2. N1 and N1 a1 and N2 a2, you can also write it as L1 and L2 as we saw. L1 is this, L1 and L2 are, you know, in the real lattice, x direction as N1 and N1 a1 and y direction as N2 a2. Okay. So L1 into L2 will be obviously the area of the actual crystal, the real lattice. So area of the crystal. And this we know that this is 2 pi by a1 and 2 pi by a2, the area of the bigger. So how many k points will be there? Total k points will be the bigger area divided by the smaller area. That will give you the number of squares in this bigger rectangle. So that will be this divided by this, and if you calculate it, so that will come out to be n1 into n2. Okay, what is n1 into n2? The total number of lattice points or total number of atoms in the real lattice. So that concept of the 1D, it still remains true in the 2D. So whenever you have a primitive, now it is 1D, 2D or even 3D. If you have a primitive cell, so in the 1D, primitive cell is simply a length. In the 2D, it's going to be an area, the primitive cell. In 3D, it's going to be some volume. The number of k points in that volume, area or length, it's always going to be equal to the total number of atoms in the real lattice, always. Okay, so that's what I was trying to show you. So this is again the 3D, the generalization to 3D. I'm not going to the mathematics, but eventually you get the same results. Okay, so now let's talk about something that we already have gone through, the Brillouin zone. You remember the Brillouin zone? In the crystal structure, we saw the Brillouin zone. So at that time, we did not know why we were studying that, but it's very important. It's an important concept. So we know the geometrical definition of the Brillouin zone. What's the Brillouin zone? What is a Brillouin zone? First, Brillouin zone is something in the reciprocal lattice. Okay, before that, do you remember the Wigner seed cell? Okay, Wigner seed cell is simply a primitive cell, right? We know that it's a primitive cell. Primitive cell, you understand, right? So it's a primitive cell, but it's a special type of primitive cell. So what we do, we focus on one lattice point, and then we look at the neighbors. We draw those perpendicular bisectors or the perpendicular bisector surfaces, and then we enclose that area or volume or whatever. Yes, so that's what my Wigner seed cell is. And Brillouin zone is the Wigner seed cell of the reciprocal lattice. If you make a Wigner seed cell in the reciprocal lattice is also a lattice. So you focus on one reciprocal lattice point, do all that procedure of finding the Wigner seed cell, and that becomes your first Brillouin zone. And then there is second Brillouin zone, third Brillouin zone. We have seen that. Okay. So Brillouin zone, the definition we already know, geometrical definition, but how is that concept useful for our band structure, or how does that relate to my K? Let's see. Again, I am going to be starting from the 1D, okay, 2D and 3D. I will simply show you the results. Derivation you can go through on your own. Okay, so say for 1D, what do I have? I have say two values of the K which differ by a reciprocal lattice vector. What is a reciprocal lattice vector in 1D? It is some integral multiple of 2 pi by a. 2 pi by a is the primitive vector, and any reciprocal lattice vector will be integral multiple of the primitive vector. M times 2 pi by m is an integer. Yes. Now I know that the Bloch wave function satisfies this equation. Okay. So I have written psi x plus a is equals to psi of x into e to the power iota k. This subscript k I am putting because psi will also be a function of k. Right. So if you look at the other definition, this psi x is equals to e to the power iota kx into u of x. So psi is also a function of k. You know that. So that's why there is this index of k here. Okay. So Bloch wave function, but Bloch wave function corresponding to which k? So that k I have denoted here explicitly. There can be several values of the k, and corresponding to each k value there can be a different Bloch wave. That's what I am trying to say. Okay, so say this is for k. Now Bloch wave function for k dash equal to k plus g. Yes, so I said I have two k values which differ by g. So one is k, other will be k plus g. Yes, and what will be the Bloch wave function? So that will be psi of k dash x plus a, psi k dash x e to the power iota k dash a. K dash is k plus g here. You substitute that and split it, so e to the power iota ka into e to the power iota ga. Now this quantity we know that from our crystal structure theory, e to the power iota reciprocal lattice into a, that gives me equal to 1. You can go back and check your notes, you will find it. Okay, this e to the power iota ga is actually equal to 1. So this is 1. So what do I have? Psi k dash psi k dash x plus a is equals to psi k dash x into e to the power iota ka. Okay. So what does it mean? Now this wave function corresponding to k satisfies this, and e to the power iota ka appears here. Right. This also satisfies this, and e to the power iota k appears here, not k dash, it is k. It means that psi k and psi k dash, they are not different wave functions, they are the same wave functions. Yeah, by comparing. So psi k and psi k dash, they represent the same wave function, or you can say psi k is periodic with the reciprocal lattice vector k. So if I change the k by g, so I get the same wave function. But what if I want to find the distinct values of the wave function? I mean distinct wave function. I mean after every g it's repeating. I don't want that. I want to know, okay, it's repeating, fine, but I want to know what are the unique wave functions that I have. Do I have some range of unique wave functions? How do I find it? Because after every g it repeats, and g can be anything, m into 2 pi by a. Okay. So let's take the smallest g possible. What's the smallest g possible? Other than 0, of course.
1.
So m equal to 1, which is basically the primitive lattice vector, 2 pi by a. Okay, that's the smallest g. Primitive lattice vector is also a reciprocal lattice vector. It's the smallest in magnitude. So if I have this is my b equal to 2 pi by a. Yes, it's the smallest one. And I have one k value here, say this. And I do, so this is k, yes, and I pick any point k dash here. The distance between them cannot be larger than b. Correct? So this k dash minus k will always be less than b. Okay? So only at the end points you can say that yes, these two vectors are p distance apart. This and this. But in between, if I choose any point, any 2 point k and k dash, the distance between them will always be less than b, or less than, you can say, g. B is also g, one of the g. So in this period, I cannot have any 2k values which are g distance apart. You get my point? So the wave functions of k and k dash, any 2k, one is k, another is k dash, they cannot repeat, because the distance between them can never be equal to any of the g, not even the minimum g, which is b. Okay, that's why the wave function corresponding to k and k dash will be always different. They will be distinct. You get my point? Yes? What do you need for the repetition? You need k plus g and k. So there must be g distance, at least g distance between them, for them to be the same. And what's the minimum g? Minimum g is b. And the distance between k and this k dash is even less than b. So it can never be equal to b or any other g. So that's why they will never repeat. Okay, so the range of k that results in distinct wave function can be limited to one primitive cell. Do you agree? So in one primitive cell, there will be all the k values will have distinct wave functions. That is called Brillouin zone. Okay. Now, does this definition and our actual earlier definition, geometrical definition, do they match? Yes, they do. What is our earlier definition? Brillouin zone is the primitive vector of the reciprocal lattice. Yes. Here I am saying that primitive lattice vector, primitive vector of the reciprocal lattice will always contain distinct values of the wave functions, right? So basically Brillouin zone can also be defined as the range in which you will always have distinct values of the wave function, distinct wave function you will have. Okay. And primitive cell, actually there is no need to particularly select the Wigner seed cell. We can select any primitive cell, but Wigner seed cell is just easier to work with. Again, okay, it's more symmetric, it's easier to work with. That's why we choose a Wigner seed cell rather than any complex primitive vector, primitive cell. You know that there can be several primitive cells corresponding to the same lattice, different shapes. But Wigner seed cell is more easier to work with. That's why we choose that. That's the only reason. Okay, so for 1D, what will be, by the way, the Brillouin zone, the first Brillouin zone. So say this is the 0, this is 2 pi by a, 4 pi by a, minus 2 pi by a, minus 4 pi by a. Yes, so this is your b. Yeah, this is 2b, and so on. So these are lattice point, reciprocal lattice points. What's the Brillouin zone here? Brillouin zone is Wigner seed cell. Let's do the geometrical thing. So how do I make that? I will focus on one reciprocal lattice point. What are the neighbors? This is the neighbor, this is the neighbor. What do? I make perpendicular bisector here and a perpendicular bisector here. What is this? This is in the middle, so this is minus pi by a, this is pi by a. So this range is my first Brillouin zone. Okay, and in this range I can pick any two k values, they will have distinct wave functions. Similarly, you can have second Brillouin zone, third Brillouin zone, and so on. But this is what the importance of the Brillouin zone is for the quantum theory of the solids. This is the same thing, but I have explained. So here I have used this definition, right? Psi of x plus a, psi x into e to the power. But you can also use the other definition of the Bloch theorem. This one, psi of x is equals to what? E to the power iota kx into u of x. So I'm just trying to show here is that, say you have psi 1 corresponding to k and psi 2 corresponding to k dash, right? So you will have u1x, which is periodic, you can see that. And u1x, by the way, it can be a complex number. So you have real part and imaginary part. I think, okay, so the blue is the real part, red is the imaginary part. Okay, and then you have e to the power iota kx, which will be like this, right? It will also have real part and imaginary part. One will be sine kx, other will be cos kx. So that's why there is some phase difference here. Okay, and the product of the two will give you the psi, which is like this, u1x into e to the power iota k1x. Now what I'm trying to show here is that when you have another k dash, say, which is k plus g, okay, so for that I know that the wave function has to be the same. I've already proved that. So this part has to remain the same. K dash is k plus g, it means it's a larger wave function. I mean, it's a larger wave vector. Larger wave vector means smaller wavelength. So that's why this is narrow. Okay. So this is not equal to this, right? But I still want the product to be the same. So this has to change according to the k. You get my point? That's what I'm trying to show here. Yeah, u1, k1 gives you this. I want the same thing here. I know that the k has changed. So u will also have to be adjusted so that the product still remains the same. So what I'm trying to say is that this u is also a function of k. So that periodic part, it is not that it remains the same. When you change k, it changes the periodic part, okay, along with the k itself. So this is again the same thing, but in general you can prove that in 2D or 3D the range of k values which give you distinct wave function, that will be confined to the Brillouin zone, okay, or the primitive cell, right? So in 1D it was simply a length, in 2D it will be some area, primitive cell, in 3D it will be again some volume, okay, and better if you choose Wigner seed cell, So Wigner seed cell we have seen. For FCC, what is the Wigner seed cell? PCC, what's the Wigner seed cell? We have seen all of those shapes and all. So they will be useful for us because we know that in that particular volume, all the K's will have distinct wave functions. Okay, one more concept before we take a break. So let's talk about something called crystal momentum. Now you must be wondering what exactly is K. In case of free particle, we know that it is 2 pi by lambda. It's a wave vector, very well defined. What is K in case of Bloch waves? So it is kind of a wave vector, right? It has some dimension of 1 by a, but not exactly 2 pi by lambda. I will show you. Okay, or in other words, we can say that you remember for the free particle, P is equals to h bar k. Momentum eigenvalue equal to h bar k. We know that in case of free particle, right? And this is what this can be related to the lambda using the de Broglie relation, and you can find out that k is equals to 2 pi by lambda. Yes. So for free particle, we already know that the energy eigenwave function is a e to the power iota kx. Is a simple plane wave, and wave vector is related to the momentum as this h bar k, and psi, this a e to the power iota kx, which is the energy eigenfunction, it is also a momentum eigenfunction because if you can actually test it, right? So momentum operator is minus iota h bar d by dx, right? You apply the momentum vector to the psi, it should generate some number times psi. Then we will say that this is eigenfunction of the momentum also. So you differentiate iota h bar d by dx, a e to the power iota kx, a you can take out, e to the power iota kx gives you e to the power iota kx, multiplication of this iota and k, and eventually you will find that it is h bar k into this thing, and this thing is your psi x. So it becomes basically some number times the wave function, the original wave function. Okay, so we can, that's why, relate this h bar k directly to the momentum eigenvalue. Now can this be done for the Bloch waves as well? Does k actually represent the momentum eigenvalue or not? Can I write k is equals to p by h bar in case of crystal? Let's see. Okay, so what do I have? I have these wave functions, Bloch waves in the crystal. Yes. So Bloch waves, if I apply this momentum operator to the Bloch wave, so what do I get? Minus iota h bar d by dx. Now I not only have e to the power iota kx, I also have u of x. Okay, you apply the chain rule, so you will get this, right? So there will be du by dx in one term, right, and then there will be the differentiation of this in the other term. So one term you get like this, other term you get like this. Okay, now this part ux into e to the power iota kx, it is actually psi x h bar k, so number times psi x, right? So p cap psi gives you number times psi minus something else, and this is a non-zero quantity. Okay, u is a function of x. There is no reason for du by dx to be 0. It's some function of x, a periodic function of x, and this is not 0. We know that this term is not 0. So p cap psi, it is not equal to number times psi. So this psi is not an eigenfunction of p cap. So you can't have k is equals to p by h bar. No, not allowed. So this k, that you see here, it is not the same k as you saw in case of a free particle. Not the same thing. Okay, Bloch waves are not the eigenfunctions of the momentum operator. Okay, but again, I want my convenience also. Okay, I know that the actual momentum does not give me actual momentum operator is not going to give me h bar k. I know that, but I can define another momentum which is called crystal momentum. So crystal momentum is nothing but it's a quantity just defined for convenience. So it's defined as crystal momentum is defined as h bar k. Okay, so this is not the real momentum, because for the real momentum this is not valid. But we can define a quantity, h bar k, which we don't call momentum. We call that as crystal momentum. Okay, so you can do that, but again, for actual momentum, it's not possible. So now we're going to study a simple model called Kronig-Penney model. Usually crystal structures are pretty difficult to deal with, can be very complex. They can have complex crystal potential, and it is not usually easy to find out the solution of the Schrodinger equation, analytical solution. Okay, so usually that will be numerical solution. You do that with the help of some software or something. Even there it's not that easy. But in the Kronig-Penney model, we simplify things and we can achieve a solution of the Schrodinger equation, an analytical solution. And this model is going to actually show you how the bands are going to form. We have now studied how qualitatively they form, but is my Schrodinger equation also going to give me the bands? That's what we are going to see. Okay, it's 1D model, but still a little complex. There will be some mathematics, so I'm going to go through the derivation. So just hang on with me. Okay, so let's start. Crystal potential of 1D crystal. So it will be this, correct? And what I'm going to do, I'm going to approximate this with this. Okay, so each of this thing, Coulombic well, it has been replaced with a square well. And the distance between, so this is your B, right, this barrier, and this attractive potential width is A. So it's a simplification that we saw earlier. Now for this square periodic potential, yes, it is possible to get some analytical solution for the Schrodinger equation. I mean, it will be an implicit equation, not explicit solution, but still at least you will, with the help of the mathematics and some approximations, you will be able to see some expression. Okay, so let's start. Because it's a periodic potential, so everything is going to repeat. So let's focus on one period, which is from minus B to A. So minus B to A repeats, yes. So period. If you ask me what's the period, so it's B plus A. So after every B plus A, it's repeating. So there are two regions in this part. So first is this region from 0 to A, which has a different potential, and from minus B to 0, it has a different potential. Okay, so here the potential is 0, and from here to here the potential is V naught. Okay, I could have assumed that this is 0 and this is minus V naught, whatever you want to do. Okay, so but in this case I'm assuming this 0 and this is V naught. So let's write the Schrodinger equation, time independent Schrodinger equation for both of these regions. Why we are writing that? Because we want to find out the eigenfunctions, eigenvalues, right? energy eigenvalues, and that will give us some idea about how the bands form and all of that. Okay, so let's start from this H psi equal to E psi, right? Time independent Schrodinger equation, and let's focus on this first, x lying between 0 and a. So this is going to give me this, the Schrodinger equation, because my potential is equals to 0, right? So d2 psi by dx. So what is the Schrodinger equation? Schrodinger equation is d2 psi by dx square minus h square by 2m plus v psi equal to e psi. This is 0, and this thing goes here, h square goes down, and then because this is minus, so you can take this thing here, so this will be plus here, right? And what will be my alpha square? Alpha square will be under root of 2me over h bar square, correct? So this 2me over h bar square, and so that gives you alpha square, right? Alpha is under root, so alpha square will be 2me over h bar square, correct? Now what kind of solutions this will have, we will see, but before that let me write the equation for minus b to 0 as well. Okay, so for minus b to 0, this is going to be this. Again, my v is v naught here. Okay, so d2 psi b by dx square plus beta square psi b equal to 0. So how does that happen? Again, so this is minus h bar square by 2m d2 psi by dx square plus v naught psi equal to e psi. You can take it here, or whatever. I mean, you can also take it here, whichever way you want. Because this is already minus, so let me write it like, so say this is e minus v naught into psi, there is a minus and this thing, so this will become d2 psi by dx square v naught minus e into psi, and there is a multiplication factor also, so 2m by h bar square. I forgot that. Okay, and if you define this as some beta square, so that's what it is. Okay, now there can be two cases here. In one case, v naught can be greater than e, right, and v naught can be less than e. Depending upon the two cases, this beta square value can be different. Okay, so if this is this, so then it becomes negative, right? If v naught is greater than e, so if you bring it on this side, so it should be a negative quantity. Beta square should be negative. And if this is say v naught is less than e, then this becomes a positive quantity. So there will be plus sign or minus sign. Right, so in general I can write beta square, but beta square can have two values here. What are those two values? This. So beta can be equal to iota beta minus, and in iota beta minus is equals to under root of 2m into v naught minus e by h bar square. So in this case my energy is less than v naught. Okay, and this is going to give me a negative sign here. Why? Because iota beta minus, beta is iota beta minus, so if you square that, so iota square will give you minus 1, right? So that will automatically give me minus beta minus square. Okay, and the other case can be when e is greater than v naught, so that will give me beta plus, and there will be simply a plus sign here. So under root of 2m into e minus v naught by h bar square. Both the cases are possible. Yes? So in one case I am saying energy is somewhere here, in other case I am saying energy is somewhere here. Okay, let's move. So let's talk about the general solution for this and this. What will be those? So general solution for psi A and psi B will be so for psi A, it means from 0 to A, right? So your potential is this, you have this equation. And this equation, you know that if I have a differential, second order differential like this, and there is a plus sign here, I get sine and cosine. A sine kx plus b sine b cos kx. Yes, that's what you get. I mean, you can solve it, from that a e to the power iota kx plus b e to the power minus iota kx. From that also you can get, but it will give you sine and cosine eventually whenever there is a plus here. Okay, and whenever there is a minus here, say that this for example, in one of the cases there will be minus here, so that will give you sine hyperbolic and cos hyperbolic x. A sine hyperbolic x plus b sine hyperbolic x. Or you can also say, so this gave you a e to the power iota kx plus b e to the power minus iota kx, or equivalently a dash sine kx plus b dash cos kx. Both of these are actually equivalent. You can prove one from the other. Okay. If I expand sine and cos, so it will be, what is sine? E to the power iota kx minus e to the power minus iota kx divided by 2 iota or something, right? So you can expand cos and sine, and then you will be able to get this. Okay. And for this, if you have a minus sign, so we have seen that if you have gone through the square potential, so you might have seen that it is e to the power what? Kx plus b e to the power minus kx. Instead of iotas, there will be kx and minus kx. And because this is kx and minus kx, so you can always convert this into some a dash sine hyperbolic x and kx, and b dash into sine cos hyperbolic kx. You can always convert. Of course, these constants will not remain the same. You will have to adjust the coefficient, but you can write these forms. So for this particular problem, I won't be working with iota and e because it is better. I mean, it is easier to work with sine and sine hyperbolic. In this particular case, not always. Sometimes we choose the other versions as well, right? Okay. So psi A is AA sine alpha x plus BA cos alpha x. Yes. So instead of k square we have alpha square, so that's why alpha. And psi B will be AB into sine beta x plus BB into cos beta x. Okay. So why I haven't written sine hyperbolic and cos hyperbolic? Because see, beta can have two cases, right? And this equation alone can specify both of them, both of those cases. How? It will become clear. So say I have beta is equals to iota beta minus. It means it is actually minus case. Iota square becomes minus. Correct. So for that, sine and cos, if you put say iota beta minus x here and iota beta minus x here, so that will convert sine and cos to sine hyperbolic and cos hyperbolic. Okay. So this thing I'm saying. So this is going to give you sine hyperbolic. You can check again. X. How you will check from this definition? So what is sine? Iota k. What will be this? So this will be iota beta x. E to the power minus iota. into iota beta x divided by 2 iota. You simplify, so iota square becomes -1, and then iota square becomes -1. So what will it give you? It will give you e to the power beta x minus e to the power minus beta x divided by 2 iota. So this is my sine iota beta x. What is this thing? This is sine hyperbolic x. Okay, so sine iota beta x is some iota times, I think, sine hyperbolic x or something like that. Okay, some constant times though. So that constant can be absorbed in the coefficient, so it doesn't matter. Okay, and if this beta is not iota beta minus, so then it's the same case as this psi a, right? So then that will become the plus case, no problem. So in general, this can represent both the cases. Just a compact form to write. Okay, now let's try to apply some boundary conditions. What are the boundary conditions? You have two regions. So this is 0 and this is A and this is minus B. Correct? This part. Now wave function has to be continuous. Where do you think the wave function can become discontinuous? I mean, this is psi A and this is psi B, right? So this is one solution, this is other solution. So we need to tie them up. The overall wave function has to be continuous. So it means psi A and psi B must be equal at this point, at this boundary. So psi A 0 must be equal to psi B 0. Yes. Second thing, their derivatives also must be continuous. This d psi A x by dx at x equal to 0 must be equal to d psi b by dx at x equal to 0. Why the derivatives must be continuous? For psi to be well behaved, continuity of psi is fine. Why the derivative should be continuous? Is it always that the wave functions have continuous derivative? Not necessarily, but in this case it will be continuous. So whenever you have a finite potential, finite V, derivatives will always be continuous. Why? Because the Schrodinger equation says so. d2 psi by dx square plus V psi equal to E psi. Now if my V is, say, finite, right? So this d2 psi by dx square, I mean E is also finite. So d2 psi by dx square will also be finite. Correct? I mean, what is d2 psi by dx square? It is, this E minus V into psi into 2m by h square with a minus sign. So that's what my d2 psi by dx square is. If everything is finite, d2 psi by dx square will also be finite. Now, if I have a finite second derivative, it means first derivative has to be continuous. Okay? You can't have a finite second derivative without the continuity of the first derivative. So that's the reason. Okay, say if I have first derivative which is like this, you have this and then you have sudden jump like this. Will the second derivative in this case be continuous or discontinuous? Differentiate it one more times and you will see infinity here. Correct? If this would have been continuous, say like this, yes, differentiated, second derivative is also continuous. The Schrodinger equation is fulfilled because my V is finite. Yes, if V is infinite, that's a separate thing. For example, a delta function or something which peaks at one particular point. In those cases, second derivative may not be continuous. So then you also remove the restriction of the continuity of the first derivative. Only in that case. Okay. So let's clear this. So So this is just the two boundary conditions I have. Okay. Now, because my crystal is periodic, so psi of x naught plus period will be equal to psi of x naught into e to the power k into period from the Bloch theorem. Yes. What is the period in this case? What is the period after which the lattice is repeating? A plus b. So in our case, the period is not a plus b, because after a plus b it is repeating. Okay. So you form this x naught plus a plus b is equals to psi of x naught into e to the power iota k into a plus b. Now let's take x equal to minus b. Right, for x equal to minus b, this and this will cancel, and what will it give me? So it will give me, this is cancelled, so it will give me psi a of a, x equal to minus b. At x equal to minus b, my psi is psi b. Got it. Okay, so this thing. So it's not psi a or psi a and psi b are just the portion. I am applying this to the full wave function. Okay, so when I have psi of a, so I will obviously write psi a of a, right? And when I'm falling at minus b, so I will obviously write the wave function value there, which is psi b. Okay, at what's the wave function at a? It is psi a. What's the wave function at minus b? It is psi b. So that's why psi a, psi b minus b e to the power iota k into a plus b. Get my point? Yes? Okay. Similarly, we can further differentiate it, this Bloch theorem, and again can put x equal to minus b, and again we'll get a relation. So you can differentiate this Bloch theorem definition and again put x equal to minus b, and you will get another condition like this. So now you have 4 boundary conditions, 5, 6, 7 and 8. Okay. 4 boundary conditions, 1, 2, 3, 4, and then you have psi a and psi b given by these things. What you can do, you can substitute 0 here, that will give you one relation. So from these 4 boundary conditions, you will find 4 relations between all the coefficients. What are all the coefficients? You have 4 coefficients, AA, BA, AB, BB. Right? So 4 equations are going to give you 4 conditions. I'm not going to go through the mathematics, you can do that on your own, but these will be the 4 conditions that you will get. Okay, just keep substituting and you will be getting this. Okay, now from 9 and 10, we can eliminate 2 more variables. Let me eliminate AB and BB. So what I can do, I can write AB equal to alpha AA divided by beta and BB is equals to BA in equation number 11 and 12. Okay, so in equation number 11 and 12, you have AA, BA, AB, BB, all the 4. Here also you have all the 4, but I can reduce it to 2 by replacing AB and BB in terms of AA and BA. So you get this equation and this equation, 13 and 14. So this 11 and 12 become 13 and 14. Okay. Now you have 2 variables to solve for. What are the other 2 variables? AA, BA, AA, BA. 2 variables, 2 equations. What is the coefficient of this? This. What is the coefficient of this? This. Coefficient here, coefficient here. So you can write it as this. So it's basically a set of homogeneous linear equations in the form of C1A1 plus C2BA, C3AA plus C4BA equal to 0. 2 linear equations, linear homogeneous equations, and you have the coefficients, you know the coefficients. Now how do I solve it? You can use the matrix method, right? So in the matrix method, what usually it is like this, ax plus b y, say a1 b1 a2 x plus b2 y is equals to some c1 c2, something like that, and then you have this Cramer's rule, right? So you calculate the determinant and all of that. So I won't go through that, but I'm going to tell you the direct condition. So whenever your C1 and C2, basically these two quantities are 0, you will only find a non-trivial solution which is not 0, it means. So you will only find a non-trivial solution when the determinant of this matrix C1, C2, C3, C4 is 0. You can go back and check the matrix theory, you'll find it somewhere. Just for this derivation, you won't be using the matrix theory in the whole course again, just for this, but the simple relationship. Okay, so the determinant of this equation, this matrix must be equal to 0. What will be the determinant? Determinant will be C1, C4 minus C2, C3. Okay, so this is equal to 0, and now you can substitute the value of C1, C4, C2, C3. You know the value in terms of those AA and not in terms of A. So in terms of those sine, cosine, big expressions. Do that, and what you do after some simplification is this. This is the equation you will get after some mathematical manipulation, and equation number 15. Now equation number 15 is interesting. What's on the right hand side? Right hand side is a function of k. A and B are constants, right? They are constants of lattice. Left hand side, it's a function of alpha, beta. Alpha and beta are appearing. What are alpha and beta related to? Energy. Alpha is under root of 2 me over h bar square, beta is something similar. So left hand side is completely a function of energy. Right hand side it's completely a function of k. So this is the equation which is giving you a relationship between E and k. Energy and the wave vector k. Yes, and it is much more complicated than the free particle. In the free particle, what was the relation? E is equals to h bar square k square divided by 2 ma square or something like that, right? The dispersion relation. Now the dispersion relation you will get but from this equation, and this is not an explicit equation. Okay, so let's simplify it more so that we can see what we want to. Okay, so let's take the case for which my E is less than V naught. I'm just going to take one case. I'm not going to discuss the case for which E is greater than V naught. So for this, beta is equals to iota beta minus, yes, and sine can be converted to sine hyperbolic as I already discussed, and cos can be converted to simply cos hyperbolic. So you replace this sine iota beta b with iota sine hyperbolic and cos with the cos hyperbolic. After doing that, you get this equation. So all the alphas will have sine and cosine, and the beta will become sine hyperbolic and cos hyperbolic. You can see that. Okay. So as I said, alpha and beta are functions of energy, and it's a relationship between k and E. That's what we wanted, but still a little complicated to solve. So what we are going to do, we are going to make some approximations. So I'm going to make an approximation that my B is very small, not 0. Okay, B is the barrier, right? So it's like this. So this is A and this is B. So B is kind of barrier between this and this. So if electron has to go from here to here, it has to cross this B. Okay, so this barrier width, I am assuming that it is very small and the barrier height is very large. So my V naught is very large and B is small, but the product of the two is still finite. That's what I'm assuming. So it's like a delta function I'm approaching. And the delta function, that's what you do. Okay. V naught is large, B is small, but the product is still finite. V naught is finite. That's what my assumption is. And that will simplify things a lot for me. So after making this assumption, what do we get? Okay. So because my V naught tends to infinity, and I know that beta minus square is 2m into V naught minus E by h bar square. So I can neglect this E in front of this V naught. So it becomes this, right? 2m V naught by h bar square, and definitely it is much greater than alpha square because V naught is infinity here, and in alpha square I simply have 2m E by h square. V naught is much greater than E, right? So what I'm trying to do, in front of this beta minus square, I'm going to neglect this alpha square. Okay, so this is gone. Other thing, sine hyperbolic beta minus b, when b is small, not 0, sine hyperbolic b minus b is actually approximately equal to b minus b. Again a mathematical, so it's simply is similar to this. Sine of x is approximately equal to x when x is small. So it also holds for sine hyperbolic x. So sine hyperbolic x, when x is small, it becomes approximately equal to x. You can determine it from the Taylor series and all of that. Okay, so higher order terms in the Taylor series, they will go away. Okay, so this becomes approximately beta minus b. Okay, so this you can replace as beta minus b, and then beta minus cancel. This will be the b, and beta minus square is this term, right? So eventually you will get this. Okay, so there will be an alpha in the bottom, so that is this alpha, and I have multiplied and divided by a. So this a and a I multiplied and divided. Why? Because I wanted to create this function. So it's a sinc function, sine x by x, right? So sine alpha by x, alpha a divided by alpha a. Okay, plus cos alpha a. So okay, so cos hyperbolic beta minus b, when beta minus b is very small, this quantity will be very close to 1. So you can simply replace this equal to 1, and b is because very small, so you can neglect it here. So this becomes cos ka. Now we have a much simpler thing to work with. Okay, so let's call that coefficient mv naught ba h bar square of the first term as p dash. So what do we have? We have this equation. So it has some right hand side which is a function of k, and left hand side it's a function of energy. Alpha is a function of energy. Yes, so let's try to plot this term and this term as a function of alpha a. So this term, it's a function, sinc function, right? Sin x by x. So how does sin x by x look like? Looks like this. Yes, right? So at 0 it is 1, from minus pi by to pi by, or from minus pi to pi it has this slope, and then it will decay on both sides. So that's a sinc function. And this is simply cos of alpha a, so minus 1, and the range is between, so this will be minus 1, this will be plus 1, correct? And the sum of the two will give you the left hand side. Okay, right hand side is very simple, cos of k, so no need to plot that. Okay, let me call this as, so this is going to be a function of alpha a, right? So this, let me write it as f of alpha a is equals to this. Okay, left hand side is this. So f of alpha is equals to cos of k. Okay, now let's try to sum this up, and let's try to find out the allowed values of energy. Okay, my k is almost continuous, I know that. Yes, it is discrete in the sense that it is 2 pi, n by na, but very small distance. So I can assume that k is almost continuous. So I'm going to assume my k is an independent variable, which is varying from some value, say minus infinity to infinity. And corresponding to each k value, I want to know what is going to be my corresponding energy. So only those values are allowed which satisfy this equation, this implicit equation. Left hand side and right hand side must be equal. Okay. So right hand side varies between -1 to 1. Yes, this. Whatever k value I have, it will never go beyond -1 to 1. Correct? So only those values of energy for which my left hand side, basically f of alpha a, is between -1 and 1 are allowed values of the energy. Okay, so I'm going to plot this, and I'm going to plot -1 line and 1 line, and all the values in between will be my allowed values. All the values outside will be not allowed. So that's what we get. So when you sum this and this up, you get something like this. So at -pi this is 0, and at -pi this is -1. So you have -1 here. Okay, and at pi this is 0, and at pi this is -1. So you have -1 here. Similarly, at 2 pi it is 0, and at 2 pi it is 1. So at 2 pi you have 1 here. So this is 1 line, this is -1 line. Yes. So f of alpha values which are lying between -1 and 1, the portions are this, 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 this. All of these are allowed. All of these f of alphas are allowed. But which k values they correspond to? Allowed is fine, but which k values they correspond to? So let's start. So let's start from Ka equal to 0. Ka equal to 0, if I put, so that will give me cos 0 equal to 1. So let me, point that here. So this is Ka equal to 0. Okay. Okay. So when I go from +1 to -1, so that's what my cos Ka is, right? Like this. Oh, I've already drawn that. So here. So this is 1, this is -1. Okay, so you start from here, 0, it is giving you 1, and when it is giving you -1, it becomes pi. So you start from K equal to 0, and you reach here, and it becomes pi. Correct? And all of these energy values are allowed. And when K varies from 0 to pi, energy is going to vary from some value to some other value. This is not allowed. This portion is outside. So this is not allowed. So you were at pi. So you again start from pi. You go from pi to 2 pi. Okay. So you were here. Here. Now you go from pi to 2 pi. So pi to 2 pi. Again, this is allowed. Yes. So this allowed value I am showing with a band. Correct. So for all of these alpha, so what is on the x-axis? Alpha A, basically energy. Alpha is energy, under root of 2 me by h square. So all of these energy values are allowed. This band. Then the next band is this, which is from 2 pi to 3 pi, then 3 pi to 4 pi, and so on. Now all of these energy bands are the allowed values of energy, and in between you see gaps. So this alpha A value which is falling here and in between these two bands, this is not allowed. Not allowed. So between the bands you have some forbidden regions. You see where I'm going. You have bands and you have band gaps. Same thing you can do on the left hand side. Okay, so it's going to give me the energy bands. How they will look like? What if I plot E as a function of K? So this is called EK diagram. Okay, and there are several ways to plot EK diagram. I will show you. So this is one of the ways. This is called extended zone scheme. In this scheme, I am varying 0 to pi k equal to 0 to pi, then pi to 2 pi, 2 pi to 3 pi, and I am assuming that energy is like monotonically increasing. Okay, but I will show you other ways also. Okay, so how it will look like? It will look like this. So from Ka equal to 0 to Ka equal to pi, it means K equal to pi by A. So from 0 to pi by A, right, alpha A varies from here to here, and alpha and energy, if alpha increases, energy increases. Alpha is proportional to root of E, right, or E is proportional to alpha square. So if I am going from this alpha to this alpha, my energy is increasing. So when I am going from 0 to pi by A, my energy is increasing. Okay, when I am going from pi to 2 pi, or you can say pi by A to 2 pi by A in terms of K, pi by A to 2 pi by A. So again my alpha A is increasing, so energy is increasing. Don't look at f of alpha, look at alpha A. Okay, alpha A is the energy, f of alpha is a function of energy. Okay, so when you are going from left to right, of course your energy keeps increasing. Okay, so at pi by A, you can see this range of energy is not allowed. What is this? This break is coming from this. So these alpha A values were not allowed, right? So this is also pi by A, this is also pi by A. So at pi by A, you have this value of alpha A, this value of energy and this value of energy, and in between you have a gap. What is this corresponding to? This corresponds to this. And then again you have similar gap at 2 pi by A. So at 2 pi by A, what do we have? This is 2 pi by A, and the next 2 pi by A is starting from here. So this gap, this is missing. No alpha A is allowed. It means no energy is allowed. And what is the energy axis? This. So no energy is allowed means I am going to go vertical here. Okay. Similarly, you can keep on plotting on the left hand side also, and this is your EK diagram. Now this is the dispersion relation. Okay, and this looks a little similar to the free particle EK diagram. Free particle EK diagram was this. And E was proportional to K square, H square K square by 2, 2m, whatever. And at K equal to 0, E was equal to 0. But in this case, at K equal to 0, you have some finite energy. K is not equal to 0. The other thing is that it was all continuous. Here you have gaps, band gaps. Okay, so this range of energy, this is your band number 1, this is band number 2, from here to here band number 3, and in between the bands you have band gaps. Now this is your first Brillouin zone, minus pi by A to pi by A. Yes? What's the second Brillouin zone, by the way? So this is the first neighbor, 2 pi. So look at the lattice point. There is no lattice point here. Here there is no lattice point. Lattice point is here, 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 and at 4 pi by A, minus 4 pi by A, you have the lattice points. And look at the first nearest neighbor. So this and this. So you draw these two perpendicular. These are called Bragg planes, if you remember. In the crystal lattice, I told you these perpendiculars are also called Bragg planes. because this is actually important in the diffraction theory also. So Bragg plane, X-ray diffraction or Bragg diffraction, right? Okay, so this is the first Brillouin zone. What about the second Brillouin zone? Remember the definition of the second Brillouin zone. So what do we do? So I have already drawn the perpendicular between this and this. So the next is this. Okay, so what will be the perpendicular bisector between this and this? This. What will be the perpendicular bisector between this and this? This. Okay, now this is also Bragg plane, this is also Bragg plane. The second Brillouin zone is the region in which you can reach from the first Brillouin zone by crossing only one Bragg plane. Okay, so this region is that region. You can reach this region from the first Brillouin zone by crossing only this Bragg plane. And you don't have to cross the second Bragg plane, so which is this. So this region is the second Brillouin zone. This region is the second Brillouin zone. And similarly, you can, this will be third Brillouin zone and third Brillouin zone. Okay. So I already told you the minimum allowed energy, the ground state is greater than 0 here. Band gaps emerge at the Brillouin zone boundaries. So at any Brillouin zone boundary, you can see, so all of these are Brillouin zone boundaries or Bragg planes. So band gaps will always appear at those boundaries. So at this boundary, you can see the band gap. At this boundary, you can see the band gap. Okay. So actually, if you look at the diffraction theory, it's because of the electron wave diffraction. So at this particular condition, for this particular, you can say, value of the K, the condition of diffraction is fulfilled. So at the Bragg planes or the Brillouin zone boundary, that condition is fulfilled. So that's why you see this this band gap here. Okay, and how do the electrons fill? There can be several electrons in a crystal, right? Several atoms. So if you have, say, one electron atom even, and there are n such atoms, so there will be n electrons and can be very large. So you will start filling those electrons from the lowest energy. So you start filling the electrons from the ground state, right? And plus and minus spin both are allowed. So in one particular energy state, you can have two electrons of different spins. That's allowed. And you can keep filling the electrons, So the highest filled band at 0 temperature, absolute 0, that is called valence band. Say you start filling these bands, there can be large number of bands, infinite number of bands I can draw. Okay, but at some point you will be running out of the electrons. So you start filling this, say from here, this is filled, say this is filled, and this is filled up to say here. Okay, so then this becomes the valence band, highest filled band, and the next one becomes the conduction band. Okay, so if this is the filled band, highest filled band, so then this becomes the conduction band. Okay, so that's how the nomenclature goes. Highest filled band at absolute 0, valence band. The band next to that is the conduction band, which is empty, completely empty at 0 Kelvin, but at room temperature you can find the electrons in the conduction band. Conduction band means it can, if the electron reaches there, it can conduct easily. We will go through that in detail later on. Okay, so conduction band, you can also say that it's the lowest empty band, because beyond that empty band there can be more empty bands, higher in energy, and the highest filled band is called the valence band. Okay, so let's quickly also see the other two schemes. So EK diagram, repeated zone scheme. So we have already seen the extended zone scheme, but let me show you the repeated zone scheme. So what we have is this, and I know that, it's a cos function, so it's a periodic function, correct? What's the period here? What's the period? Some 2 pi by a. Okay, so if I have, say, k, and k plus 2 pi by a, or an integral multiple of 2 pi by a, I'm going to get the same result. Okay, period of the cos is 2 pi and the coefficient of k is a, so that's why 2 pi by a. So replacing k with k plus 2 pi m by a, it's going to give you the same RHS. You can try that. So let's put cos of k plus 2 pi m by a, right? This is going to give you cos of k. Multiply this, so a cancel, this will be ka plus 2 pi m cos of x plus integral multiple of 2 pi gives you cos of x. Okay, so that's why this. So if that's the case, for cos ka, or you place the k with k plus 2 pi m by a, for k and k plus 2 pi m by a, right hand side remains the same. Yes, so you get the same value of the alpha, same allowed value of the alpha. Right hand side is not changing. Yes, if right hand side remains the same, so you get the same value of the alpha. So same alpha can be get from the k as well as k plus 2 pi m by a. Okay, alpha is a function of k. You know that, because when you change the k, you change the alpha. But k and k plus 2 pi m by a are giving you the same value of the alpha. So I can say that alpha is then a periodic function of the k, because I get the same value of the function after a period. What's the period? 2 pi by a. Period or multiple of the period gives me the same value. Okay, alpha is the function. What is it a function of? It's a function of k, and it's a periodic function of k. Okay, so if it is a periodic function of k, you know what? So this value I assumed k equal to 0. But why k equal to 0? It could be 2 pi by a, it could be 4 pi by a, 6 pi by a, whatever. I mean, if I use 0, 2 pi by a, 4 pi by a, 6 pi by a, I can get the same one. I can get the same corresponding value of alpha. Right? Similarly, for this value, 0 was varying from, it was varying from 0 to what? Pi. But why only pi? If I use pi or 3 pi by a, 5 pi by a, 7 pi by a, I can get the same value minus 1. Yes? So there are several ways to plot the same information. So what will my EK diagram then look like? See, alpha becomes a periodic function of k. So energy will also become a periodic function of k. Correct? That's how it will look like. You have one particular band. This we have seen. Okay, from minus pi by a to pi by a. Yeah, this will be my energy. This will be my energy. But this part, see, when I come from say here to here, my alpha is changing. My energy is changing. Right? Say I'm going from 0 to pi by a. So 0 to pi by a. Okay. So, and again, if I go from 0 to minus pi by a, so this branch I can plot. But it's a periodic function. So this portion it's going to repeat. So this is repeating. The same portion I have replicated here, same portion I have replicated here. You can repeat it. So it's called periodic zone scheme. Similarly, for this band, this is going to simply repeat. Similarly for other bands. So this is also something which you can use. Not very commonly used, but there are certain concepts that will be helpful to if we use the repeated zone scheme there. We will take an example in which this scheme is going to be helpful. Okay, so the last scheme is the reduced zone scheme. Well, you know that this is a periodic function. Yes. And the same thing is going to repeat everywhere. So why to plot that? I can simply plot my information from minus pi by a to pi by a, and then it is understood. It's just going to repeat. So I can simply reduce my information to this region, minus pi by a to pi by a, because I know that this is going to just repeat. It's just periodic, and this is the same information. Okay, so this is called reduced zone scheme. Reduced zone scheme means I'm limiting my k values to the first well-known zone. Okay, so I just cut it here, and I know that this is just going to repeat. So why to plot? This, it's enough. If I have to plot, yes, I know that this is just going to repeat. Okay, so this is called reduced zone scheme. This is we will be using very frequently, and this is very commonly used in the EK diagrams as well. When you say, people give you say EK diagram of say silicon, germanium, so they are usually using this reduced zone scheme. Okay, but any of the scheme is perfectly fine. You can use any of those.